All right, well, thank you everyone for joining Flex Train, a training opportunity brought to you by Johnstone Supply. I was originally going to do this class as a CFC slash HCFC. I've decided that I think I'm going to separate those and extend this out into next month a little bit so that I can talk about each class of refrigerants individually. I think it's very important to understand the differences of refrigerants and where they came from and why they changed. Because as I started going through the CFC, I had a lot of fun going through this section of refrigerants. You know, last week we talked about the pre-CFC refrigerants, all of the refrigerants from the 1800s that brought us up into the modern mechanical revolution, the industrial revolution, and then into the 20th century. And it it really is important to know why we continue to make changes with refrigerants and why, as we go forward, even today, we're still doing the same thing. We are still hunting for that ideal refrigerant, that refrigerant that gives us both performance and efficiency, and it is safe for the environment and safe for us. And it's been a struggle to find a perfect refrigerant. And so far, that has not happened. And so we've made changes along the way. So I think it's very important to understand each refrigerant classification individually. So today we're going to do chlorofluorocarbons, and then we'll follow up next week with HCFCs, and we'll continue on through. We'll do HFOs and HFCs, and we'll do some HCs as well. So a lot of different refrigerants. And the neat thing about refrigerants is the progression that has happened with those and how they have changed our life. If you remember last week when we were talking about pre-CFC refrigerants, we developed refrigeration for the purpose of manufacturing ice. Because at that time, we were manually harvesting ice out of frozen lakes and streams and ponds, and we were transporting those to do our refrigeration of our perishable goods. And that's really all we were doing. It was replacing that harvesting of ice with a mechanical process using refrigerants like ammonias and CO2s and ethers and all these different chemicals that we had available to us, and some that we had developed along the way. The problem with all of those is they had some negative consequences. They were flammable, they were toxic, they were high pressure, all sorts of things. So that got us up into the early and the mid 1920s. And as the demand for residential refrigeration developed, so did the necessity to have a safe refrigerant. Because remember, when we were talking about, some of the refrigerants like methyl chloride and some of these very toxic refrigerants, they were good refrigerants, but they were not safe to have in our homes. So in the 1920s, we sought to find a replacement for those toxic refrigerants. And along came this development of chlorofluorocarbon refrigerants. So getting away from all of these toxic and acidic and high pressure refrigerants. And in 1928, a chemical engineer by the name of Thomas Midgley Jr. created the first non-flammable, non-toxic chlorofluorocarbon refrigerant. And it was labeled as Freon well, there's a whole class of refrigerants, but R12 was that original Freon. And so it was trademarked. The name Freon was trademarked at that time. And so it was owned by DuPont Chemical Corporation and is now owned by Chemours. And Chemours is still a major manufacturer of refrigerants, a good friend of the show. They actually are the patent owners for the R1234YF, which we're seeing in automotive air conditioning systems, and we're going to see it blended with R32 here in just another year or two. There's going to be the new refrigerant that we're going to see. We'll talk about that a little bit later. So R12 has been around for a long time, and the whole Freon name was because of these new refrigerants, these non-flammable, non-toxic chlorofluorocarbon gases, and it was branded Freon. So it included an entire class of refrigerants that were CFCs, HCFCs, HFCs, but it all started with R12. So our original refrigerants in the CFC class were going to be R11, R12, R123, and R502 as the dominant refrigerants of that time frame. So 1928 is when we developed R12. We had a variety of other CFCs that were in that time frame and moved along through the next couple of decades, and they all had different purposes. So if we look at R12, I know this picture is a little bit blurry, but this was a really good representation from National Refrigerants of the uses and applications for these different refrigerants. So if we look at R12, that's the white one, that was used for automotive air conditioning, it was used for medium temp refrigeration, and it was used for high temp refrigeration. So that was our coolers and our freezers in residential and light commercial and light industrial applications. R12 was the dominant refrigerant of the time. We had R500 that was being used in commercial and industrial air conditioning. That's the yellow one. R502 was a really common low temp refrigeration. So when we got into the commercial and industrial walk-in freezers, we were using R502. But R12 could be used in a lot of these freezer applications. But if I needed to keep very low temperatures, I would actually end up going to R502. So if I was trying to hard freeze ice cream, I would use an R502 application. We had some others like 503 that got used for some very low temp applications, very industrial chiller style applications. We had R11 that was being used in centrifugal chillers. So that's where we moved from the dialene that was created by Carrier into now our new CFC R11. So R11 was that first chiller refrigerant. And we had like 113 and 114 that had some specialty commercial and industrial uses. But this was our primary CFC refrigerants of the day. And it was really an interesting way that we did a lot of charges on these critical applications. So if you think about a smaller refrigeration unit, we had to have a way of charging those. And we didn't have the scales and the techniques that we have in modern refrigeration. We actually had things like the old dial a charge. And so this was actually just donated to me yesterday by my son Matthew, by his grandfather, who got me into the industry a long time ago. And we were talking about where this program is going and the education that we're doing. And I asked him about the old dial a charge, because I actually learned on this piece of equipment, 20 some years ago, almost 26 years ago almost. Wow. Anyhow, so in that time, things were very, very different. With this charging cylinder, as you can see, very interesting piece. We actually talk about that in our EPA prep class, how to recover refrigerant from these if you're still using those. Hopefully you're not. But what we would do with those is to measure the charge in it. We had to know what the refrigerant was. So this particular one is made for actually R12, R22, and 502. I think this one is. Yeah, no, 500. So what you would do is you would actually hook your refrigerant jug up to the tank. At the bottom of it has a valve to open and close, and you had a vent valve at the top. And so you would open your vent valve, and then you would open your supply, and liquid refrigerant would fill up inside of the cylinder. And then you would actually have a charge gauge that would tell you, at this temperature, here's the level that my refrigerant is going to be. So if I needed a 1 pound, 6 ounce charge of R12 refrigerant, I literally filled R12 up into my cylinder until I got to the line that said, this is your 1 pound, 6 ounce mark for this temperature. And some of these even had an electric heater that was connected to them. So when we were charging it into the unit, we'd plug in the electric heater, which would create higher temperature, which increased the pressure and force the refrigerant out of the cylinder. Very, very different techniques than what we have today. But that's how we started this. So let me take a quick poll real quick. I have a couple things for everyone today. We have a poll, and you should also have it in your material drop down. You should have a little video, which we're going to play here in a little bit, YouTube video, but it's pretty interesting. So let's take a quick poll here. And the poll is, how long did we use R12? Let me launch this and get an idea, because it's been around, remember, since 1928. So was it 20 years? Was it 40 years? 60 years? Or 80 plus years? I'll give it just a minute or so while we're taking a poll. Any thoughts? Some shy people this morning. There we go. Now we're getting some answers. All right. Survey says around 60 years is the most common answer. And I would have expected that. I think in 1928, knew that we had gotten into the Montreal Protocol and had some changes in the industry. What I find was kind of fascinating, actually. So CFC R12 went into use in 1928, and it was the most common refrigerant used. It was banned in 1996. So the Montreal Protocol came along, we banned the production of it, we stopped its manufacturing, and we had a total ban. I didn't even realize it went this new until I was doing the studying for this. We had a total ban worldwide in 2010. It was supposed to go out of production in 1996, but new supplies were allowed to be used until 2010, and then we had a complete ban. The interesting thing about it is it was such a commodity and still maintains its usefulness in some places in the world that there has actually been an underground production of CFC R12 even till this day. We had large shipments of it confiscated as new as like 2014 in Russia that were being manufactured in China disguised as ethylene glycol containers. And I found reports as new as 2019 where we were still confiscating newly manufactured, illegally manufactured CFC R12 that was coming out of different places around the world, primarily China. So it has been definitely 80 plus years, almost 100 years that we have been using R12 refrigerant. So when R12 came to the scene, it revolutionized our comfort level. So the first applications of R12 air conditioning systems actually went into automobiles. So in the late 1920s and into the early 1930s, we were experimenting with adding air conditioning systems to these beautiful new luxury automobiles that we were manufacturing. So the first ones were actually installed in places like the floorboard of the vehicle, where we were running electrically operated air conditioning compressors that were running off from inverters, off from the engine, generators off from the engine that was producing a higher voltage that we could operate a compressor with. And sometimes we even had a large battery that had to be charged, and that battery operated the compressor for our air conditioning system. And so we had these large air conditioning systems being put into our vehicles and became a new comfort level. We were adding these in the 1930s. The most common one was Packard. Packard was a very, very luxury vehicle of its time. They spared no expenses when creating their custom vehicles. So air conditioning then got developed into an engine-driven compressor so that we were using the serpentine belt of the, well, it's a V belt of the engine to drive an open drive compressor mounted to the top of the engine. Picture on the left is an original photo. Picture on the right is a fully restored Packard with that same layout. Very similar to my 1930s Tecumseh compressor that is actually sitting on the shelf over here by me. See, very similar design to that, and that's a 1930s Tecumseh there. So we were moving into air conditioning in our automobiles and increasing our comfort level. We even had add-on air conditioning systems that bolted onto the back of your custom motor vehicle so that we could supply air through the rear of the cab. Can you imagine having that thing bolted onto the back of your vehicle? But that was a very expensive custom item of the time. That was some of our first aftermarket custom air conditioning systems in the 1930s. We were also starting to see home portable air conditioning systems like the one on the left, and we were also getting General Electric building these compact and built on air conditioning lines. So we were now having portable and stationary air conditioning systems being introduced in the home, and that exploded. So you got to think, we had very uncomfortable situations. If you think about the heat and humidity that we had in our homes in the summertime in the 1920s and 1930s, when air conditioning came along, we could decrease the temperature, we could control some of the humidity, and we can now make life indoors more comfortable. And that moved an entire new generation of demand. We were even using R12 as our propellant in our aerosols. So the one on the right, luster net, so we were using our, ladies were using hairsprays that were powered by R12. The one on the left is actually, if you look at that, that is an insecticide, a handheld insecticide for when you're outdoors so that you could remove insects in the air with Freon R12 propellant. So R12 quickly became the staple of our daily life. By the 1940s, we were mass producing portable window air conditioners that could be moved from room to room. If you were having guests, you could take it from your bedroom and put it into the living room and condition that space. We were adding air conditioning into our bus transportation, our city bus transportation in the 1940s, increasing the travel across the country. We started introducing it in the late 1940s into our movie theaters. And the movie theaters have always been a place for people to gather and enjoy the new live video productions and stage productions. And it became a very important part of the growth of the inner cities as they were developing. Our theaters were a major place to gather and organize. So when we introduced air conditioning into some of those in the 1940s, it went crazy, because before that, the only air conditioning we had were swamp coolers. I've actually worked on one in an old theater in Franklin, Indiana. A swamp cooler would just bring well water up, run it over a layer of baffles, and blow a fan across it. So it would cool the air, but it didn't do anything for humidity. If anything, it would increase the humidity. So it may be cooler inside, but clammy. So when we introduced air conditioning into these, now we're able to control the temperature and control the humidity. So they were a very, very important gathering place of the time. By the 1950s, we were having whole room air conditioning systems. So these were stationary units that could sit indoors and have the condensed air pumped outside. We were getting into custom refrigerators. We were getting into quality air, or what we know today as IAQ. We were introducing electronic media cleaners into our air conditioning systems in the 1950s. So now we were getting to the point where we were getting so used to air conditioning that it was a part of our daily living, to the point where we started adding filtration into those in the 1950s. And as we created these new atmospheres, we created a new level of comfort that had not been experienced before in the hot summer days. So we now turned our homes into a year-round livable quarters, where before we spent a lot of time outdoor during the summertime, a lot of time on our porches. We had a lot of time allowing breezes through our homes and naturally ventilating. By the 1950s, we were adding air conditioning to our systems. And by the late 1950s, we had companies like Westinghouse that was actually starting to produce whole house air conditioning systems, where you could leave your house closed up and conditioned year round. Now, if you look into your materials section, GoTo Training isn't very good for playing videos, but I found a very interesting refrigerator advertisement from 1951. As we were doing this mass production of refrigerators, we started doing frost-free refrigerators from 1951. So if you want to go to your materials section, and you'll have a listing there for 1951 refrigerator. Go ahead and pull that up, and it's about 2 minutes long. It's worth the time. Let's watch that together real quick. Anybody out there had a non-frost-free refrigerator? I used to have a 1950s GE that I restored early 2000s. I'll leave that there. You'll have this linked into your materials. You can come back and watch that later. 1950s, we're getting into custom air conditioning, custom refrigeration systems. By the 1960s, we were adding air conditioning into our airplanes, our commercial jetliners. We were adding air conditioning into our metro trolley systems. So subways were getting air conditioning, so it increased the mass transit around the United States. And by 1969, more than half of all newly manufactured vehicles were equipped or had the option of air conditioning by 1969. So CFCs have been around for a very long time. They were introduced because they were non-flammable, non-toxic refrigerants. And we came up with a new classification for those. So when the classification system came out for refrigerants, for CFCs, HCFCs, we had to give a number so that we could continue the production and the development of refrigerants and have a standard, a national and international standard. So what we did is we developed a numbering system that accounted for the different atoms inside of the molecule. So what we were doing, and it's a little confusing, but bear with me for a second. So a special numbering system was to be used for fluorinated alkalines prefixed with Freon, or R classifications, where the rightmost value indicates the number of fluorine atoms. The next value to the left is the number of hydrogen atoms, but it is +1 because there's no zeros in this classification. You won't have like a R102, it'd be an R12. So there's no zeros in here. So you'll have a 1 if there is a zero atom in it. And the next value to the left is the number of carbon atoms, =1, because remember, no zeros. So like R12, for example, indicates that so almost all of these are some derivative of methane. That's where carbon base is at, is our methane derivative. And it contains 2 fluorine atoms. So that is the 2 on the end. And there's no hydrogen. So it's 0. So we're going to add the 1. So the 1 is for the no hydrogen. 2 is for 2 atoms of fluorine. Little confusing. There is another equation that gets substituted for that all the time. If you take the refrigerant number and you add 90 to it, it will give you a breakdown of the different atoms inside of that molecule. So the value of the equation is always a 3-figure number. An easy example of that is R12. So if we take 90 plus 12, so our 90 plus our R12, that equals 102. That would tell us that we have 1 atom of carbon, 0 atoms of hydrogen, and 2 atoms of fluorine. And so then we have 2 chlorine atoms resulting in a C carbon, Cl2, 2 atoms of chlorine, F2, 2 atoms of fluorine. So R12 is actually 1 carbon, 0 hydrogens, 2 fluorine, 2 chlorine. Hence the name R12. And all those R refrigerants follow that same classification principle. 2 chlorine, 2 fluorine. So our original CFC refrigerants are these, from R11 all the way down through R225. And all the numbers are based on the atoms inside of that molecule. The thing with chlorofluorocarbon refrigerants is they solved our problem of flammable, toxic refrigerants, high pressure refrigerants that we previously had. And so they became very popular to the point that it changed our standard of living. The downfall of the chlorofluorocarbon refrigerants took a very long time for us to discover. The downfall of chlorofluorocarbon refrigerants is their effect on the ozone layer. So it wasn't until the 1980s and definitely through the 1990s that we were starting to notice a change in our atmosphere, in the stratosphere. We were noticing a decrease in the amount of ozone in the stratosphere. Ozone is molecules that has 3 oxygen atoms, and they are used to help shield us from ultraviolet radiation. They're what comprise most of the stratosphere, so we call it stratospheric ozone. What we discovered as we started measuring these changes in the stratosphere and this hole in the ozone layer, we started looking for the source of it. And what we found was that the chlorine molecules in our chlorofluorocarbon refrigerant was very much the culprit in our ozone depletion. So what happens with a CFC refrigerant molecule as it enters into the stratosphere? Ultraviolet radiation penetrates through. So before it gets to the stratosphere, as it's on its way, CFC refrigerants, the chlorine that is bonded to those carbon molecules are not very tightly bonded molecularly. So ultraviolet radiation has the ability to penetrate through the CFC refrigerant molecules in vapor form and allow the chlorine molecules to separate off from that chlorofluorocarbon molecule. So as that chlorine atom separates from that CFC, it then bonds with the ozone molecule. Remember, that ozone molecule has 3 oxygen atoms. So the chlorine atom, that now free chlorine atom off from our CFC refrigerant, will bond with that ozone molecule. It'll actually bond with the oxygen atom individually and has a connection to it that is stronger than the bond that the oxygen atom has inside of the ozone molecule. And it separates one of the oxygen atoms away from the ozone molecule. And so now that nice trifecta of oxygen atoms inside of that ozone molecule is broken apart. And what we have from that is 2 new molecules. A chlorine monoxide, so a chlorine with 1 oxygen atom, and a diatomic oxygen. Neither one are catastrophic, but the downfall is that we've destroyed the ozone molecule, which had the ability to reject ultraviolet radiation. So now we're allowing ultraviolet radiation to penetrate through the stratosphere and down into the lower Earth's atmosphere. And what we find is that a single chlorine atom off from that chlorofluorocarbon refrigerant can last in the stratosphere for up to 120 years and can destroy up to 100,000 ozone molecules in the process. So this is what NASA and other research agencies around the world had finally discovered by the 1980s and 1990s. So then it became a matter of, we love our refrigerants, we love our air conditioning, we love our refrigeration. So now we need to come up with something different. These chlorofluorocarbon refrigerants have been getting dumped into the atmosphere and destroying it. And so now we have to come up with a conclusion. So chlorofluorocarbon refrigerants became popular because they were a non-flammable, non-toxic replacement to our previous generation of refrigerants. And after 60 years or so, we started realizing that they were actually very damaging to the Earth's atmosphere. So we had to make some changes. And so we started looking for some options. And next week, we'll start diving into what those replacement options were. Does anyone have any questions, any comments on chlorofluorocarbon refrigerants that we used from the 1920s all the way up and through the 1990s and banned in 2010 worldwide? Okay, well, hopefully I've answered everyone's questions. I really appreciate you all joining us this week, and I look forward to seeing you next week when we talk about HCFC refrigerants. Everybody have a great day.